So,
okay.
All right. Before we start, let me introduce Dr. Fazio. So, Professor Fazio is a senior research scientist at ICTP in Trieste, Italy. His main research field of interest are mostly quantum transport in nanostructures, superconductivity, quantum simulators, non-equilibrium dynamics of many-body system, and quantum information processing. And today, Dr. Fazio will talk about collective effects in quantum heat engines. So, Dr. Fazio, the stage is yours. You can start.
Okay, thank you very much. Sorry, probably you saw some photos. I don't know. I tried to switch my telephone and something, but now I think it's okay. So first of all, thanks a lot.
Sorry, we don't see your screen. I think something happened with the screen sharing.
Okay, so I try again. So now it should be okay, right?
Yes, it is.
Okay, so I hope it works. So first of all, thanks a lot for the invitation. I'm really glad to participate to this conference. Although it's online, so only, but okay, I really appreciate to be part of this event. And as the chairman said, I'm going to talk about heat engines, and I slightly modified the talk because depending on the time, in addition to talk to discuss about collective effects, I would like to say,
Dr. Fazio, we hear your voice with some noise. I think it's better to switch off your video. Probably there is some problem with your connection.
How do I switch the video?
Just click on the, or let me, if I can, I switch it off for you. Okay. I switched it off for you. I think you.
Okay.
Yeah, it's switched off. Yeah. Start the presentation again.
Okay. So, and please just give me a warning, say 5 minutes before the end, because I cannot see the time.
All right, no problem.
Okay, so I'm going to talk about heat engine. As I said before, in addition to collective effect, if I have time, I would like also to say something about some geometric aspects which are maybe interesting in this context. So before I go to the talk, I would like to acknowledge a very fruitful collaboration that we had with people in Pisa, Fabio Taddei, and our student Vivek Bandari, with Felix von Oppen in Berlin, and most important with Liliana Racea in Buenos Aires. For what concerns the collective, and this is related to the geometric effects, but the thing I would like to say about collective effect in heat engines is also work that I've been doing with Gonzalo Manzano, was postdoc here at ICTP in Trieste, now is in Mallorca, and with Fernando Iemini and the student Leonardo da Silva Sousa. So if you're interested, these are works that were published say some time ago, and they're both on the archive. So having said this, let me start by just starting by introducing very things that we all studied in first year in our university. That is, so what is the heat engine? And actually, quantum heat engine is not much that different. So we have a system which I will call a working fluids, which is connected to reservoirs kept at different temperatures. And as we all know, then there will be some heat flow from the reservoirs in and out through the system, and this machine is able to perform some work, or some work is done on the machine, for instance, in the refrigerator and things like that. And this is, so far, there is not much quantum in it. But let's say in the last decade or so, people got interested in understanding if by substituting the working fluids with a quantum system, then special effects might arise due to the quantum properties of the working fluid itself. And there are several reasons why this type of questions might be of interest, and people essentially refer to this case, the case in which working fluid is just a small quantum system, as quantum heat engines. So as I said, there are several questions that may be interesting for fundamental reasons, but also for possible applications in quantum technologies or in technologies in general. So essentially, people are interested in understanding how to realize small heat engines to dispose on somehow control heat transport at small scale. But also there are some fundamental questions that people try to answer in this context that are, I think, let's say, curiosity driven, but are quite important because they are connected to the essence of the dynamics of quantum open system. By having a working fluid which is made of a small thing, the smallest possible thing that we can imagine is a two-level system, we can ask if, let's say, what we know about heat engine still applies at this small scale. So if there is any limit to the performance of thermal machines which are related to the size. There's been a lot of discussion, and I think it's still an interesting question which has some aspects which are still open. That is, what is quantum in this machine? So in the operation of this machine. So is quantum dynamics important? For sure, any working fluid will have quantum correlation presence, but this does not mean that the operation itself of the machine needs quantum mechanics. And what does it mean? It needs quantum mechanics. Is quantum mechanics, or some of its aspects like entanglement, are important, or even on the opposite, detrimental? We know that quantum information processing, quantum technologies are based on the idea that quantum dynamics may lead to processes in manipulating information or transferring or simulations that are much more efficient than their classical counterpart. Is this also true for
Dr. Fazio, we lost you. I think there was some problem with the connection.
Do you hear me now?
Yeah, I hear you, but I don't see your screen.
Okay, I don't know what happened. Is it okay now?
Yes?
Okay. So I think sorry, I just repeat. Please tell me if I mean I was talking about collective. So together with the quantum aspect, I think it's also important to understand how there's I mean what is the connection between the small small engines that I was mentioning before, and how do this approach the macroscopic limit, and what is the scaling. So if some cooperative effect may lead to some enhanced performances. There is another aspect that I will not mention in my talk, but I would like to, so I will not touch on my talk, but I would like to mention at the beginning, because I think it is very important. It is related to the whole field of statistical physics. People refer as fluctuation relation, Jarzynski relation. So if you have again a working fluid which is a small quantum, is a small system, then differently from the microscopic case, then both their heat exchange and work performed will fluctuate, and the fluctuations may be comparable with the mean. So typically in the macroscopic standard thermodynamics, we forget about fluctuation of 1/n or effect. But when the machine scales down, then fluctuations are relevant, and this is fundamentally, in the case of quantum systems, fundamentally related to the fact that transfer of energy occurs in quanta, and so essentially in a cycle, for example, the heat that is exchanged may fluctuate strongly, and so there is all this part which is also very important, but I will not touch. I would like to connect the initial motivation that I gave you by considering two examples of heat engine, which they both touch two of the aspects I mentioned before. And so I will first discuss actually the second example, which is I will discuss the case in which the working fluid has some collective properties. So there is some quantum dynamics of interacting systems, just to understand how collective effects will affect the properties of the performance of the thermal machine. And second, if I have time, I really would like also to talk about just a quantum system connected to the reservoir, which is driven through a cycle adiabatically. We know that when a quantum system is dragged along adiabatic in a cyclic fashion, then there are geometric properties which emerge, I mean, very phase, just to mention, which are related to the path that the wave function perform in some parameter space. And well, it turns out that a heat engine that operates under this condition will have properties that do depend on the geometry in this parameter space, both work and heat exchange, but also dissipation. And this is a way to see truly quantum mechanical effect appearing in the context of small engines. So I will start with the collective effect, and this is something that has been discussed in several papers. Some time ago, together with Michele Campisi, we just, for instance, looked at the question that, let's say, in which situation in which collective behavior manifests, let's say, in full glory. That is when the working substance is close to a phase transition. And a way to characterize these properties is just to look at how work is done by keeping the efficiency constant. And the delta eta that I'm referring here is just the deviation from the Carnot efficiency. I mean, there was here, so we were interested also in understanding if it was possible to reach Carnot efficiency at finite power, but for the time being, I really would like to see if it is possible to have some collective enhancement. And one can imagine to consider a very simple auto machines that is just actually is slightly different from what we know in macroscopic case, but just mimic exactly the idea of thermalization, compression, thermalization, and expansion. And compression and expansion is nothing else than just considering an Hamiltonian which in which the level separation is changed uniformly by this parameter lambda. Now, without going into much detail, then it turns out that the output work has very nice relations to the it's actually is proportional to the heat capacity or to the specific heat of the material, which means that if you have a system which is on the verge of a phase transition, the specific heat will have kind of divergence or singular behavior, and hence this collective effect will reflect in the properties of the heat engine. Let me stress that so far this is not necessarily anything related to quantum, so this will occur at any level, both for classical or quantum systems. And but there are many effects in which the role of interaction in the working fluid is truly related to quantum properties. So people have been looked at the boost in the performance through quantum phase transition. There are actually also interesting aspects related to the fact that you can do cycles by modulating the interaction between the constituents, the particles, and this is something you can do only using quantum simulators, but so it's not, I mean, it's difficult otherwise, and by this interaction-driven process, you can implement cycles which are not standard, if you wish. And last but not least, there is one aspect which still needs to be fully understood, but I think it's very interesting. That is having a working fluid in which there is a phase with broken time translational symmetry. Broken time translational symmetry is something which goes also under the name of time crystals. And time crystals are essentially a coherent motion of the system. So it's a kind of, if you wish, synchronization of the quantum system. Having a broken time translational symmetry may be particularly important in just creating kind of resonant effect in the transfer of heat, and hence strongly modify the performance of heat engines. And I should say that there is really a number of very relevant papers, and I'm here not listing all of them, entirely concentrating on the properties of interaction and collective behavior of heat engines. So a simple model that one can study, which works, I mean, of course, it's idealized, but let's say it is very nice for several reasons, because, for instance, it is in many regimes essentially analytically exactly solvable. It is a model that we study with Gonzalo, Fernando, and Leonardo. It is just two clouds of spins, let's say, which are kept at different temperature. So they are both connected to different reservoir. The left, they are connected to a cold reservoir, and the right cloud connected to the hot reservoir, and they are both interacting. They are both interacting through their collective properties, through their collective spin. So this is, so I want to stress, this is just just a model whose merit is to be able to study crossover from a single spin to a macroscopic behavior. This is pretty, I would say, so I would say it's non-trivial, and the trick that makes it possible is that the model is built up on the interaction between collective spin system, this capital S here. Also, the coupling is through the coupling of the two clouds to the reservoirs is through the collective spins, and the different temperatures of the two reservoirs is just included in the different, I mean, it's pretty standard. It is included in the different rates, gamma down and gamma up, through the distribution of the bosonic bath. Now, as I said, the properties of this simple heat engines can be studied to a large extent analytically. So we don't need to confine ourselves only to small system, but we can go from single qubit to very large system, and both regimes are analytically solvable, because so either you have a small Hilbert space or in a semi-classical limit, and in between we can just do some exact kind of type diagonalization of calculations, and essentially one has to extract heat current, power output. Let me show some results that I would like to highlight. So first of all, so essentially, depending on the splitting of the two of the spin the two level systems in the two clouds, then and you can operate this machine as a heat engine or a refrigerator. I would not focus on this. Rather, I would like to focus on the central, for the discussion of today's talk, I would like to focus on the central panel in which you see that the power output is shown as a function of the number of spins. Then you see that these are power law. Sorry, I did something wrong and now I don't know how to. Okay, sorry. Okay, now I did it. Okay, and then you see that this power law shows you that if you increase the number of spins, then it's not a linear increase in the power output, but it may increase with an exponent alpha, n to the power alpha, which is larger than 1. So when the exponent is larger than 1, then you see that the output power benefits from the collective behavior of due to the interaction between the spins. Due to the time, I will skip this part, which is related to time crystals, but if somebody is interested, I would be happy to discuss, and I will just devote the last 15 minutes to geometric properties of heat engines. And as I said before, the idea is just to have a regime in which truly quantum effects emerge. I mean, this is something that we know very well, that is the seminal contribution of Berry in the 80s, showing that if you take a system, a quantum system, and you drag it on a cycle, along a cycle, say, just imagine a magnetic field, then at the end of the cycle, the system, the wave function will acquire a phase which is just independent on the time it took the system to complete the cycle, but it's just related to the path in the parameter space. Now, in transport, geometric effects have been studied since the seminal paper by Taules, and are related to the fact that in the same way as this classical pump, if you have a small region and kept in contact with different reservoirs, but all of them at same chemical potential and temperature, by changing the parameters in a cyclic way, it is possible to transfer charge energy through the system. And the pumping of this charge or mass or energy is connected to the geometric phase. There are, I mean, the list of theory and experimental, I mean, especially theory paper, very, very long. Let me only mention this experimental work by the group of Pecola, because if I have time, I would like to connect to this. There is one other aspect which is also important and very interesting, related to geometric effect in heat engines. That is trying to understand what is what are geometric phases in quantum open system. While it is very natural to understand quantum, so geometric phases in closed system, say in open system, there are several issues which are important to be, I mean, that make it an important difference. That is, first of all, there is no natural, adiabatic limit, because, I mean, eventually the level spacing gets blurred by the coupling to the environment. There are a lot of issues which are very important. They're also very important because people have been discussing geometric quantum computations, and there it is important to understand how geometric computation is affected by noise and imperfection. All this brings to the study of adiabatic driven thermal machines, because they combine all these aspects that I mentioned before. So thermal machines, quantum thermal machines are important in quantum technologies. They are open systems, so one can understand the properties of open systems, and they are connected to the efficiency of quantum protocols. And by just looking at time periodic changes, a cycle in this thermal machine, then we can really understand all these aspects. So eventually, let me stress that when we talk about the thermal machine, we are talking about flow of energies, heat, and work. And this means that this will have something very clearly related to the pumping effect, both of mass, charge, and energy. Last but not least, let me stress that this type of concept that I would like to briefly sketch can be realized also in experiments. And these are related work that I would like to mention. So without going in too much details, then an adiabatic quantum thermal machines work exactly on the same principle as before. So you have two baths, hot and cold, but the only difference is that now the quantum part that form the working fluid is driven by some along a cycle by some change in a set of parameters. So for instance, if you have a spin, this will be the magnetic field will change in time, but let's say this type of thing. And what is important is that the changes should be sufficiently slow so that one enters kind of adiabatic regime. As I said before, also in this case, one should look for heat transport, I mean, which flows through through the system, between the system and the reservoir, and there will be some work which may be positive or negative depending on the operating modality of the engine. Now, from how to approach this problem, I think it is interesting to use formalism, which was developed originally by Lattinger, that allows to introduce to discuss heat transport by introducing some kind of gravitational fields which account for the thermal bias. And so the key is just to do an adiabatic expansion of the current and or the force, and this has been developed also previously in different contexts by other people. The point that I would like to stress is that in this situation, then all the properties of the thermal of the heat engines are encoded in this geometric tensor. So mu and nu describe the component of the various parameters that are changed. M is and N are the instantaneous eigenstates with probability Pm determined by the mass steady state of the master equation, and epsilon are just the level. Now, all the properties are encoded in this geometric tensor, which has a symmetric and antisymmetric part. Let me go first to the antisymmetric part, because this is something we know, we just identify easily. If you take a single M, this is nothing else than the Berry phase. Now, since you have an open system, basically you will have just weighted over the probability to have a certain occupation. The symmetric part is related to absorption. So it's just you see this delta of transition between different eigenvalues, and it is related to dissipation. So this geometric tensor allows you to describe both the heat transport, the heat current, which will have a contribution which is related to pumping, and a contribution, so and if there is a thermal gradient, an additional contribution which is just related to the conductance, which scales like the period. It allows to determine the output work, which will have a part which is related to the geometric tensor again, and the part which is proportional to x dot square, which is related to frictions. So this tells you that essentially all the properties of the engines are, and especially the heat to work conversion, is rooted in this geometric term. The fact that there are frictional forces, essentially it is related to the, it's connected to the fact that, the efficiency will be smaller than the maximum attainable frequency. There is an interesting aspect related to this. That is, sorry, this I will skip. That this has been discussed very recently in this paper by the group of by Liliana and other people. That is in this geometric approach, it is possible to finding optimal protocols to maximize power generation by just looking at the kind of optimal path in the parameter space. Given the time, I think I will skip this example, but just mention that a possible experimental proposal is very close to what it is actually realized, already has been realized in the group of Jukka Pekola, that is, it is possible to realize by superconducting nanocircuits in which one has essentially a single junction with connected to two loops that allows you to change the Josephson coupling. And this in turn should be connected capacitively to two resistors, two circuits that allow to measure for heat exchange. So in Jukka experiment, in Jukka Pekola's experiment, this was the what was realized. It's just a single squid. So by just having a two-coupled squid, then with a small additional complication, one can test this geometric concept. And with this, I think my time is over. I try to sketch, to just to say a few things about two aspects of quantum heat engines. One, which is related to collective effect or the effect of interaction. There is one thing which I would like to stress, because I think it's still open, but it is worth to be explored. It's the use of time crystals in heat engines. And second, I just mentioned geometric description of adiabatic machines. And with this, I thank you for the attention. And I should apologize for all these technical problems that I had. Thank you.
Okay, thank you very much, Dr. Fazio, for the interesting talk. So we have time for questions. So if you want to ask your question, please rather raise your hand so that I could activate your mic, or just write in the chat box. Okay. We have a question by Dr. Kolachi. So Dr. Kolachi, go ahead, please.
Thank you, Professor Fazio. Now, I think I have missed the point about what you mean by geometric. I can see that there is a cycle that to give you the Berry phase. Of course, we have a heat engine and it has a cycle. But please explain more, if you would.
Yes. So yes. Sorry. So you have so you may have a cycle, and just imagine that the cycle is done slowly. I mean, slowly as compared to the typical time scale of the system. Then at some point, you will have that for instance, the charge. Let's consider this example: the charge or energy that has been transferred through the system. So first of all, may be independent on the bias. So you may have a transported heat even independent on the bias. So even if the bias is zero. And most important, the sides, the magnitude of the transported energy is just proportional to the path, to the cycle you did in parameter space. Okay, so you can essentially show that there is an intimate connection between the energy that has been transported and the phase that has been, the geometric phase that has been accumulated by the working fluids during the cycle.
Okay, thanks. I have something to think about. Thank you.
Okay, so Dr. Abdinpur, I think you also have questions. Please go ahead.
Charles, do you hear me?
Yeah, hi.
Thank you for this very nice talk. I was wondering if your working flow is something which has topological non-trivial behavior. Do you expect something strange there?
Yeah,
or?
yeah, that's very interesting. That's very interesting point, because, for instance, if you have topological system, and, for instance, you have a gap, in principle you can have I think, I mean, so we did not study this, but I think it should be interesting to be studied, because we have the feeling that you should have, for instance, kind of topological properties of the thermal machine. So it's kind of so, for instance, you may reach Carnot efficiency because losses are strongly suppressed, exponentially suppressed. I mean, this topology will appear directly on the operating mode of the machine, which will have a kind of topological protection in its performance. But we did not study. I think it's an interesting direction to explore.
Okay, so there is also a question with Dr. Shahbazi. Please go ahead.
Thank you for your nice talk. My question is related to the efficiency of quantum heat engines. My question is that if it is possible theoretically to violate the Carnot theorem by quantum
No. I think it's so thermodynamics is safe in the sense, so there is no violation. Actually, so for instance, if you take these fluctuation theorems, they are somewhat kind of, you see that from there you again find second law of thermodynamics. Yeah.
Okay, thank you.
Okay, I think there is also another question from Dr. Najafi. Please go ahead.
Professor Fazio, thank you very much for this very nice talk. My question to you is about the role of fluctuation-mediated forces. I mean, like Casimir forces. How do such forces, or how can they affect the performance of an engine fundamentally? Are you neglecting such forces, or such forces are present in your point of view?
So that's a difficult question, and I'm not sure I will be able to answer. So first of all, I'm neglecting this. I mean, so I think that in terms of fluctuations of vacuum, I'm not considering this. However, so let me say that there is, in this system, like in circuit QED, there have been experiments of actually they were done on superconducting resonators with the flux, with the squid at the end, and the squid was modulated. And this resulted in just having a cavities which was changing the length, and so in this way, so Casimir effect was measured in these cavities. And now these superconducting resonators can be used for heat engines. So I think it would be interesting to see how this will affect the engines, but I don't know how it will affect because we did not consider it.
Thank you.
Okay, we have we have time for one last question, if there is. All right, let us thank Dr. Fazio again for such an interesting talk.
Okay,
So,
thank you very much. Thank you for. Okay, bye-bye. Thank you.
Bye.